events.
Yeah.
So,
And you can, if you click on attendee, you can see the list of names. So you can.
I don't get attendees on my.
Oh, okay. But a lot of people, I'll mention in particular Slobodan has connected. So we'll say hi to Slobodan. He can't speak back to us, so which is
I
unfortunate.
I swap it on.
Okay, I think things have stabilized enough for us to start. Sam, is that your view?
Yeah, yeah, whenever you're ready, we should be good to go.
Hi everyone. I want to welcome you to this online talk in the Center for Philosophy of Science. This is a very happy occasion because we get to welcome back one of the long-standing friends of the center. I'm going to ask Allan to be patient just for a moment while I make some announcements about coming events. Of course, you all know that next week is the spring break, so there will be no talks, but we're coming back in full force the following week on Tuesday, March 19th. Shan Gao, presently visiting in the center, will give a talk on the title, What Does Quantum Mechanics Tell Us About Reality? I'm looking forward very much to the talk, although I have a slight fear that question will dictate a very short answer. Then on Friday, Nicole Younger-Halpin will be giving the annual lecture series talk. Again, it's another talk that I think our physics contingent will like very much. The title is Field Notes on the Second Law of Thermodynamics from a Quantum Physicist. And then, of course, I'll remind everyone that on April 5th to April 7th, the Senior Visiting Fellows Conference on Revitalizing Science and Values will be held here in the center. Good. So now I can turn to the really, really happy job of welcoming Allan Franklin, today's speaker, back to the center. Allan is such an accomplished scholar that I'm going to have to beg his indulgence. I'm not going to be able to do full justice to all of his achievements. But let me say just a few things. Allan is, of course, a long-standing friend of the center. He was a center fellow in 1986. And that indeed is when I first got to know Allan. And I'm a little horrified to think that 1986 is nearly 40 years ago. And we've been in touch ever since. And Allan has been in touch with the center and with everyone here ever since. So he's really, truly a friend of the center. Most significantly, he was the senior visiting fellow in 2013 and 2014. So we really had the privilege of seeing a lot of Allan then. Now, the most important thing that I can say about Allan's research is that he is a founding figure in the philosophy of experimentation. He's written very extensively on that, and his books truly form the central corpus that anyone who's interested in philosophy of experiment truly has to read. I was going to give you a count of the books, and I started searching around trying to count out how many books Allan has written, and I eventually gave up because I was really rather afraid that I'd miscount. I'm just seeing someone has got a raised hand. Is there some reason for that raised hand? Okay, I think we'll leave it. If the person with the raised hand has an urgent issue, please email Sam, and and he will be able to look after that. So the number of books he's written are so many that we've had to quell the rumor that Allan is not a person, but actually a committee. Now, I think seeing him in the flesh might help us realize that is a scurrilous rumor. It is Allan, and it's just one guy who's writing all these books. I've scanned through the list of titles. The first one is, of course, that's pertinent to this series, is The Neglected Experiment, which he was working on, I think, in 1986 when he was a center fellow. The title says it all. It's an alert that there's been a neglect by philosophers of science to experiment, and we should take it more seriously. And then the books just kept coming after that. Experiment, Right or Wrong, The Rise and Fall of the Fifth Force, Can That Be Right? Essays on Experiment. So it goes on and on. I'm flipping the page here. What Makes a Good Experiment? Reason and Roles in Science. a joint book with Ron Lehman, one of several, Measuring Nothing Repeatedly, and then, of course, the famous historical works, the Poor Richard's Almanac, the invention of the lightning rod. And then finally, we come to the book of 2018, titled, Is It the Same Result? Replication in Physics. Allan, would I be correct in inferring that there might be a connection between that book and the talk that you're about to give? Because there seems to be the same title.
It is indeed the same stuff.
Okay, then I'll hand over to you, and anyone who wants to hear more after this, I think would do well to go and look at the book. So you should take over the screen now with your slides. And while he's doing that, I'll remind everyone that when the talk is over, if you want to ask questions, you should write your name in the Q&A tab, and we will promote you to Symposia so you can be seen and ask a question.
Okay. Well, recently, that's the last few years, there's been a fair amount of anxiety because of a lack of replication of experiments in psychology and some of the social sciences. The work of the Open Science Collaboration, where they took 100 experiments published in leading psychology journals and tried to replicate them and succeeded fewer than 50% of the time. But those of us who work in physics should not feel very smug or morally superior, because for reasons I will discuss, things are not perfect in the realm of physics. But this problem of replicability has even extended to the humanities. Last year, I saw a notice of a conference on replication in the humanities. I don't know what that would mean. It certainly doesn't mean plagiarism or copying the book. The closest I got was the story by Jorge Luis Borges, Pierre Maynard, the author of the Quixote, where a 20th century writer takes as his task the rewriting of Don Quixote without actually looking at the book. So, nevertheless, I'll stay with physics, which is what I know a little bit about. Replication is regarded very highly within the scientific community. Here's a standard statement: replication and the conclusion from one study obtained independently in another is considered the scientific gold standard. Now, this is not a totally new idea, the idea of replication. I found a reference to it in 7th century Assyria. And here, Sennacherib, king of Assyria, was worried about the reliability of the people who made predictions of the future from looking at sheep entrails. And so he wrote a letter to his son. He said, he said, in order for me to set straight the divination, I divided the diviners into 4 groups to make a divination for me. May you do as I did. I have made known my clever procedures that previously none among kings had done. This was actually an example of asking for independent confirmation. It's an example also of blind analysis. So it's something that has been around for quite some time. Now, the argument, which actually John Norton made, was that if it's a correct result, it should show up when it's done again, assuming the experiments have been done correctly. I will have adopted in my work a broad definition of replicability. It includes repetition, the performance of an experiment with the same or almost the same conditions. Then reproducibility, where you require the measurement appear under changed conditions. And I also include experiments performed with different apparatuses and/or experiments that examine different phenomena that bear on the same theory or hypothesis. This is just a matter of pragmatics. This is the way I think replicability is talked about in physics. And so I will give you, there are possible problems. For example, if you exactly replicate an experiment and you make a mistake, like overlooking a confounding factor, you will replicate the result. They will just both be wrong. Ian Hacking pointed out that nobody actually wants to repeat an experiment. They want to do it better. A long time ago, Colin Howson and I argued that different experiments provide more confirmation than the same experiments, and sometimes once can be enough. The famous experiment by Wu, Ambler, Hayward, Hoppies, and Hudson showing non-conservation of parity in weak interactions, or the discovery of the positron by Carl Anderson based on essentially one photograph. And then there is the possibility of a bandwagon effect, where later experiments tend to get the same result as earlier experiments. And I will talk a little bit about that. Now, I will be presenting examples of successful replications, the discovery of the Higgs boson, the discovery and detection of gravity waves, failed replications, tests of the fifth force, a modification of gravity, and measuring big G, the Newtonian constant of gravity, and then some problems large and small with physical constants and properties of elementary particles. And then 2 case studies, if I have time, low mass electron-positron states and the pentaquark. Now, so I will begin with the discovery of the Higgs boson. Now, here, if you talk about the discovery of the Higgs boson, one does not merely find the Higgs boson. One sees something that might have been the Higgs boson, and then one counts the number of times one has seen something that might have been the Higgs boson, and one compares that number to how many times one would have seen something that might have been the Higgs boson if, in fact, there was no Higgs boson. And if the difference is large enough, 5 sigma in the high energy physics community, then one probably has found it. You'll notice that the person advocating this method, which is, by the way, absolutely correct, is Ned Stark, one of the truly honorable characters in Game of Thrones. And in the discovery of the Higgs, there were 2 experiments, the CMS collaboration and the Atlas collaboration. They were announced simultaneously, finding the Higgs. Here's the result. This is the Higgs boson going to 2 gamma rays. And what you see here is things that look like the Higgs boson if there were no Higgs boson. And here's the little signal showing you the Higgs boson. That's in the Higgs going to 2 gamma rays. Here's the Higgs going to ZZ star, where the Z is the Z boson. This is not the signal. The big thing on the left is not the signal. The signal is right here. And it shows up a little bit better when you do a little more selection on the quality of the events. And here you see, oops, the results from the Atlas collaboration. Again, you see a bump at 125 GeV. This is, again, the 2-gamma decay. And here is the ZZ star. And they have lower background for the Z, but here's the Higgs boson at 125. I think this is, in fact, a clear example of a successful replication. In fact, it's hard to say which is the original and which is the replication, since they were announced simultaneously. Okay, my second example is the discovery and detection of gravity waves. And in 1975, Hulse and Taylor noticed something very interesting. They were observing with a radio telescope a pulsar, and noticed that the period of pulsation was varying. From this, they inferred that it was part of a binary system, and they also suggested that it might be emitting gravity waves, since it's a very dense gravity system. But the effect you see is actually quite small, and so they had to wait till they could make a measurable difference in the period of the binary pulsar. And in 1981, Taylor and Weisberg reported the result. And here's the results from Taylor and Weisberg. General relativity just defined as 1. Here is the result that they got experimentally, 1.04 plus or minus 0.13. In agreement, none of the other competing theories, Brand-Sticky, came close to giving you a correct result. As time went on, things got even better. Here's the change in the period. It's 10 to the minus 12 seconds per second. Since we only have pi times 10 to the 7th seconds per year, you have to wait a fair number of seconds to see anything useful. And theory and experiment agree quite nicely within a standard deviation and a half. And then here's the history of the measurements of the change in the period. And as you can see, if you didn't know these were honest measurements, you might think it was fudge. They fit the theoretical curve precisely. Now, this is an interesting point. You have successful replications where the numerical value is in fact different. And I claim this does count as a successful replication. So those are the two examples. Now, I want to go on to a failed replication. Oops. This is, I need to tell you the other successful gravity one. This is LIGO. This is a 4-kilometer long Michelson interferometer. This is what the signal looks like as a function of frequency. This is the actual signal they observed on their detectors. You have 2 Michelson interferometers, one in Hanford, Washington, one in Livingston, Louisiana, and they're separated by about 1,100 miles. And the signal has to be, to compare them, shifted and inverted because of the alignment of the interferometers and the fact that the gravity wave hits one before the other. It's about 7 milliseconds difference. And what they did was to check on whether this is a real signal or not. Of course, notice that the signal looks pretty much the same in the two detectors. What they were able to do is to shift their detection in one of the Michelson interferometers by a certain amount of time to see how many accidental coincidences they would get. And the answer is they get almost none, one every 20 years or so. And so here's how they did it. Here's the search, and here's the GW 150-914, the gravity wave signal. If you use a generic transient search, namely the using a kind of general signal, you find it's 4.6 sigma. If you use a signal binary coalescence, namely two black holes coalescing, you find it's greater than 5.1 sigma. That's the standard of being able to say you have made a discovery in both high energy physics and in gravity waves, and pretty much nowhere else, even in physics. This is partly due to the fact that there were, in the late 60s and 70s, claims by Joseph Weber that he had found gravity waves, which turned out to be incorrect. If Weber had been correct, LIGO would have lit up like a Christmas tree as soon as they turned on. So now for the failed replications, which happens. Oh, those are the ones I showed you were the two most famous experiments in the 21st century. They're cited hundreds, if not thousands of times. I want to show you one of the least important experiments in 20th century physics, which has been cited, according to Google Scholar, 5 times in 54 years. So you can say it's not exactly high on the list. In 1969, my colleague Richard Sokash and I decided we had a clever way of finding the anti-neutron proton cross-section. Anti-neutrons are hard to make a beam because you can't focus them or separate them using electric fields or magnetic fields. And so we did it and got a result. We knew we wouldn't get a very good result. It would be very crude with a large uncertainty, but we thought even a crude result with a large uncertainty was better than no result. Okay, so it's published in 1969. Fast forward some 40 years, I'm working on a totally different project, and I find a group that has done the same experiment with very different apparatus. We use bubble chamber, they use spark chamber. And two questions, they did it a lot better. Two questions came up. One, did they get the same results as we got? And two, did they mention us? And happily, the answer was yes. And here it is. Here's the Harvard group, and here the blank spaces are our results. And they mention Franklin et al. That is, in fact, me. Okay. So now on to failed cases. This is the measurements of G, the constant in Newton's law of universal gravitation. And I don't have to make much of an argument that these don't agree. I mean, here's one of the best measurements. It's out here. Here's another good measurement, and they're, more than 4 or 5 standard deviations away from the average. In fact, it might lead you to believe that there is no universal constant. I did find a very odd paper in my work. Somebody claimed to have found a correlation between the measurements of big G and the length of the day. But later work, both theoretical and experimental, showed that they exaggerated the claim. Okay, another failed replication. Here you have a whole series. This is from 2014. I could add more. Was the fifth force in gravity. In 1986, Ephraim Fishback, Sam Aronson, and their collaborators proposed a modification of Newton's law of universal gravitation. They added to the potential a term alpha e to the minus r over lambda, where alpha is the strength of the fifth force and lambda is its range. Alpha was like 1%, and lambda was of the order of 100 meters. Now, measurements of gravity up to that time actually allowed this, and there was a gap in the measurements which allowed the fifth force. And so you also needed a local mass asymmetry to detect the fifth force. So in early 1987, there were 2 experiments, one by Peter Tieberger and one by the Etwash collaboration at the University of Washington, headed by Eric Adelberger. And they're published back-to-back in Physical Review letters. And let me show you the results. Here's the result from Peter Tieberger. He was using a copper float in water, and if there was a fifth force, the float would move away from he did it on the Palisade Cliffs in New Jersey, opposite Manhattan. The float would move away from the edge of the cliff, and it does. He resets it. Here's along the parallel to the cliff, and there's clearly an effect. But as some humorists said, all Tieberger's experiment showed was that any sensible float wants to leave New Jersey. So then there's the Adelberger-Etwash result. There's the theoretical prediction, and here's the data. They used a torsion balance with beryllium and copper, and they see nothing. And so these are clearly a failed replication. It gets resolved over the next 4 years. Actually, the experiments are still going on, but they are now more tests of the weak equivalence principle in general relativity, the universality of free fall, that all objects fall at the same rate, regardless of their mass or their composition. Here's this is the 15 experiments done in the next 4 years between 87 and 91. Not one of them finds any evidence for the fifth force. One of the more important ones was done by the Bizzettis on a hillside in Italy, using the same kind of float experiment as Tieberger did, and they see no effect. So it's a again, a failed replication, which is solved by a series of successful replications. So it does happen. Okay, now let me go on to some problems, large ones and small. Okay, here's a measurement. It's from the review of particle physics by the particle data group. They don't tell you what the quantity is. I have a suspicion, but I can't verify it. It's a measure, and what they find is the average. It looks pretty good, and the average is 0.006 plus or minus 0.18, but they scaled the uncertainty by a factor of 1.3, because when you do chi-squared analysis, you get a confidence level of about 11%. And this is actually a pretty small one for most of them, their measurements, but they recognize that measurements are going to disagree, that doing experiments is not easy, and it's hard to get all the confounding factors and such. Okay, but there is a history to this. From the late 1920s until the 1950s, the value of physical constants, like the charge of the electron or Planck's constant or the speed of light, was determined by Raymond Burge at Berkeley. He would gather all the published results, make judgments as to how good they were, and publish a value for the constant. In 1943, Frank Benford wrote a very critical article criticizing Burge. It's actually pretty nasty too, because what he found was that the values that Burge gave in 1929 and the values he gave in 1941 differed by considerably more than the uncertainties he quoted, and that the odds against such a change being statistical was ranging from 1 part in 10 to the third to 1 part in 10 to the 10th. And he suggested quite nastily that Burge might worry about the distinction between accuracy and consistency. Burge responded politely, saying that he did understand the difference and that he talked about what became known as the Burge ratio, the ratio of the external uncertainties, namely different experiments, to an internal consistency, namely the uncertainty in a single experiment. If that ratio was large, it indicated the presence of systematic effects, which are notoriously difficult to find. And so, he was more worried about the bandwagon effect, namely that people will look, if they get a result that disagrees, they will look for the source of error and continue the search until he gets close to the accepted value. Then he stops. And so that he's worried more about the possibility of people agreeing more than they should. Okay. Here's an interesting example. This is the history of eta plus minus up until the 1970s, from when it was discovered in 1964. On the left, you see measurements, it's the CP violating parameter in K-long decay. You get values that all agree with each other within experimental uncertainty. The uncertainties are getting smaller, and the mean is 1.95 plus or minus 0.3. After 1973, you get 4 new measurements. There have actually been many more since then, but they are at 2.27 plus or minus 0.3. That's a more than 7 standard deviation effect. The chance of that being actually a statistical fluctuation is 1 in 10 to the 14th. It could be that this is the first observation of a GRU quantity. Or is it BLEAN? I don't know. Where it just changed, but it's clearly a set. You have a set of consistent replications and another set of consistent replications. The current value is close to the newer value. So it's a lot better. Okay. And this is from, again, the particle data group. This is actually a plot as a function of time of world averages. And what you can see is, although there are significant changes, they tend to stabilize. And the particle data group says, by and large, however, a full scan of our history plots show a dull progression toward greater precision at central values, quite consistent with the first data point shown. We conclude that the reliability of the combination of experimental data and our averaging procedures is usually good, but it's important to be aware that fluctuations outside of the quoted errors can and do occur. So replication or successful replication is not necessarily regarded as highly here because you expect changes given that experimental techniques may happen and people may find new sources of confounding factors. There was one case in, I think it was in the 1930s, where the speed of light measured using a certain technique changed a lot. It was where you had a light source and a rotating mirror, and you measured the time between the signal were going out, and by knowing the speed of the rotating mirror, you could determine the time. And people worried about the time. But the speed of light changed by a considerable amount. And it turned out that there had been an earthquake in California, and the distance actually changed, which was something they didn't worry about at the time. Now I want to talk a little bit about more complicated cases. The first one of these is the observation of positron lines or low mass electron positron states. In the late 70s, theorists suggested that in heavy ion collisions where the charge of the two ions was greater than 173, you would produce electron-positron pairs. And because of the binding energy. And, sorry, I missed. This is 2 successful replications, neutron lifetime, and 2 different methods, and they're all consistent with each other, but they differ by 8 seconds. Nobody knows why. Okay, in this positron search, there were 3 different groups, and they all observed pretty much the same thing. There were difficulties, but here you have U-238 on U-238 at certain energy, and they see the positrons, but at certain angles, they see evidence of lines, of more positrons with a certain energy than just this smooth curve you would expect. And they worried a little bit about this. In the first publication in '83, first of all, one must show by further analysis that the structures are not produced by some yet unknown background effects associated with one of the events selected criteria. And secondly, the reproducibility of the effect has to be shown. So they were worried about replicability, but they were also worried about selection criteria. In experiments, nobody ever uses all of their data. They always make selection. And one of the problems one worries about is whether or not the result you get is an artifact of your selection criteria. Okay, and as time went on, the 3 groups continued to work, but here's a comment in a later paper. Now they're using uranium on thorium at a slightly different energy. Actually, the effect didn't show up in all collisions and in all energies, but they make subsets of data where they select on beam energy, heavy ion, scattering angle, and E plus or E minus time of flight, chosen to enhance the lines. So they are manipulating their selection criteria to enhance the effect that they see. And Greenberg, who was, I think, with the EPOS group, said with any kind of new phenomena, you try to see what conditions would optimize it. Obviously, not having theoretical guidance, we tried various things that would optimize the appearance of the peak. Now, this is fine at the beginning of an experimental search, but there are techniques for checking on whether or not your result is an artifact of the selection criteria. And here's the results that they got as of toward the end of the 1980s. They see lines at totally different energies. And the consensus was among those who worked on it that these 6 were the same line, these 12 were the same line, and these 4 were the same line. There were only 3 lines. Now, anecdotally, I did an unscientific brief survey among my colleagues on the 6th floor of Gamow Tower at the University of Colorado, and their view unanimously was that this is just random lines. Okay, so people start working on detecting both the electrons and the positrons, and the experimental apparatuses improve considerably. You're getting far more events. And here's the data. This is an example of U-238 on thorium. Here's the data. And here's what they would have seen, this peak, if the earlier result was correct. And they do it for the 3 lines that had been observed. And it's fair to say that the data are in disagreement. And finally, the thing that convinced most people that it was not a real effect was the fact what the EPOS2 group did with the improved apparatus was they had so much data they could divide it in half randomly. And what they found was that they manipulated their selection criteria and generated a 6 standard deviation effect on half their data, and applied the same selection criteria on the other half of their data and saw nothing. And the general view was that these were not real effects, that they were effects of the selection criteria. Now, things get a little more complicated with the discovery of the so-called pentaquark. Again, an elementary particle. 4 groups find evidence for a particle because of the way it decays. It has to be made up of 5 quarks, hence the name pentaquarks, and these are fairly significant effects. And they agreed with a theoretical calculation at the time. And so people further investigated it. And finally, you got 10 different groups finding the same effect at quite significant statistically and at roughly the same mass. Here's an example of one of them. This is the peak of the pentaquark. And the particle data group in 2004 said it is difficult to deny a status of 3 stars. The highest rating is 4, and a place in the summary tables for a state that 6 experiments claim to have seen. Nevertheless, as discussed above, we believe it reasonable to have some reservations about the existence of the state on the basis of the present evidence. Part of the difficulty, again, was the question of selection criteria. Another problem was that the mass of the particles that people observed did not really agree. Here's done by my colleague, Kevin Stenson. He plots the mass and does the chi-squared for agreement with the average, and he finds the probability of the results being in agreement is 1.6 times 10 to the minus 5. So they were kind of successful replications, but maybe not. And here's one example of one of the experiments. When they make more selection criteria, you see the effect. You don't see it in the full data set. But here's one of now, the problem was also that there were other experiments. In fact, there were 10 other experiments with much higher statistics. Here's the results of one of them. As you can see, you have thousands of events, and they don't see any evidence for the pentaquark. Here's again an early experiment where you see an effect at the pentaquark. Here's a much later experiment with much higher statistics. In fact, this experiment had 1,171 events. This experiment had 227,000. and they see no effect. And finally, the particle data group in 2008 says the only advance in particle physics thought worthy of mention in the American Institute of Physics Physics News in 2003 was a false alarm. So what do I conclude here is that successful replication is a goal of science and can be a standard, albeit not the gold standard. It is not always easily achieved, nor is it easy to tell if a replication has been successful or not. Successful replication demands knowledge and judgment. It is not algorithmic. Thank you.
Thank you, Allan. I'll applaud on behalf of everyone. If you want to undo the screen sharing so we can see. Thank you. That's excellent. I'm seeing applause coming in. Now, the system, as I indicated earlier, is if you want to ask a question, please write your name in the Q&A box that you see at the bottom of the screen, and I will promote you to a panelist. And so let's just wait a moment while we wait for some questions to come in. Don't be shy if you want to be put in the queue. Now is a good time to write your name in the Q&A box. Okay, I'm going to go to the first speaker. So Troy, you are live. If you turn on your video and sound, we'll see and hear you.
I think I can't turn on my video, but if you can hear me.
We can hear you, yes.
Yeah. So there was mention of blind analysis in physics, which seems to me quite similar to what's called pre-registration in the social sciences. And although they are not exactly the same, but I take it that the motivations for both of these things are similar. And the status of pre-registrations in the social sciences is, I think, still debated. So my question is, what about physics? Like, is blind analysis something that is widely used and seen as required for a study to be credible?
Yeah, I didn't mention this, but in the various high energy physics experiments, they set the values of the selection criteria before they do any analysis of the data. So there can be no hint of manipulating the criteria to get a certain result. This is one of the techniques of blind analysis, namely setting the criteria before, and it's similar to pre-registration. I thought from reading some of where I admit I haven't followed the discussions in social science at all recently, but that's essentially the same kind of thing of setting selection criteria and setting what you're going to measure and how you're going to answer it, which is, I think, a good thing. Of course, the statistical requirement for a successful result, a positive result in social science, is 2 sigma. In high energy physics and gravity, it's 5 sigma. And given that the estimates of uncertainty may be, shall we say, more positive than they might be, it's perhaps not surprising that replication doesn't occur, successful replication doesn't occur as much, but still, what the open science collaboration found was that there were just way more failures. And one hopes for better, but I noticed that Jacob Stigenga is going to be at your conference in April. Will that be available online for us? Or
I don't know.
well, Jacob wrote a quite marvelous book called Medical Nihilism, which he points out that a lot of the drug and testing is just hopelessly inadequate. Of course, he uses Bayesianism, which you might object to, John.
Okay, there's room in the Q&A list if people want to join, but in the meantime, I certainly have a question for Allan. In fact, I was kind of expecting this to appear, so forgive me, I'm going to take you back 40 years. Once upon a time, there was an idea in the literature known as the experimenter's regress, which basically said that any any experimental result was in effect tainted, because you could only believe a result if the apparatus you use was working properly, but you would only know that it was working properly if it produced a good result. Now, I think you can see that has an immediate application to the idea of replicability. Replicability is going to become automatic because people just keep adjusting their, things until they get the result that they want. Now, I know you have views on this matter. Is it now so ancient that that we no longer?
No, I regard it as probably one of my most important contributions, namely the epistemology of experiment, that there are ways of determining whether your apparatus is working properly, independent of what the result is. Now, it's true that one of the strategies, and at last count, I think I was up to 9 different strategies, was independent confirmation. But for example, there's the Sherlock Holmes strategy, which Wendy Parker thinks is the most important. Namely, if you can eliminate all sources of or all sources of background, all plausible sources of background, and all alternative explanations, you can trust your result. You can also calibrate your apparatus. The LIGO experiment, but I call it an experiment, not an observation, but it's a hybrid, calibrates their apparatus using a laser. They make sure that they see a change in the interference pattern if they move the mirror with a laser. And so that's an important point. And you can talk about, for example, the theory of the apparatus, which is independent of the theory of the phenomenon. And that can add to your view. So there are a whole set of strategies. And of course, I have argued publicly and privately with Harry Collins, although we do have a joint paper on the early gravity wave things, which, as the late Paul Humphreys said when he heard we were collaborating, and somewhere in hell, a snowball isn't melting. So,
Your talk of LIGO and replicability reminds me of one of the great lost opportunities. You said it exactly right. The LIGO apparatus is a huge Michelson interferometer, right? The biggest we've ever built. So it gave us the chance to actually replicate the old Michelson-Morley experiment, right? At vastly greater accuracy than ever before. So I did wonder whether this had been done, and so rather than leaving you hanging, I actually found out what was going on. So I had the opportunity to talk to some of the LIGO experimenters, and the answer is the following: yes, in principle they could do it, but it would be tremendously burdensome in their data analysis, because what they do, and in the early stage of processing the data, is that they filter out any diurnal periodicity in the data, right? Because they're looking for signals of a very much shorter period. So so it's there if they are willing to go back all the way to the very rawest data, if they still have it, and try and look for a diurnal signal and then demonstrate its absence. I have another question, but I'm a little concerned that we have 26 attendees who I'm sure are eager to ask questions, and I don't want to cut them out. So I see Slobodan Perovic is joining us, and I'll bring him in.
Hello.
Hi.
Hello.
We hear you, we don't see you. Is that by design?
Yeah.
Oh, wait, I
Okay. Hi, Alan.
Hi, sir.
So thanks for the interesting talk. Lots of examples, new examples I didn't know. So one question that sort of came to mind as I was listening to these examples is basically when you compare, normally the replication is sort of used almost synonymously with reproduction of the results, let's say. So if you have a different fairly different apparatus, then you don't really expect to reproduce the whole process, right? You might get sort of confirmation of the hypothesis or a theory, but surely some of the parameters will be different, and your explanation of the phenomenon that you are experimenting with will be, and the outcome will be different. So for example, if you use back in the days, when astronomers started using reflectors as opposed to refractors, telescopes, they surely had to explain why are they seeing the same objects that they are seeing at the sky. Then when the radio telescopes came, there was a whole fuss actually about in the early days of radio telescopes, whether really what they're seeing is the same, are the entities that could be potentially detected in the optical part of the spectrum, whether they really know where they are located, and so on. So I'm wondering, there seems to be sort of a subtle but very important distinction in terms of what apparatus one uses and how different it is from the previous apparatus when we want to talk about replication and when we want to talk about reproduction of the results and all the changes in the conditions under which the phenomenon is observed. So I'm wondering whether you have any actually thought, because it seems to me that much of the confusion, even in social sciences, might be due to the fact that these two get actually conflated very often. People don't really pay attention to the instrumental part of the sort of theory experiment or theory observation interface.
Yeah. I mean, I think my answer is it depends on how the different. For example, the case I gave of the neutron lifetime, where you have the magnetic confinement as opposed to the neutron beam, which differ by 8 seconds, and nobody knows at this point why they differ. In fact, and people, speculate, well, maybe it has something to do with magnetic fields, although nobody has any way of explaining it. And so the thought is to do it a third way. Somebody is proposing doing it in space. And so I think, it is something one needs to worry about. But for example, in the case of LIGO and the Hulse-Taylor-Weisberg observations of gravity wave, I think there is enough context, again, background knowledge, namely general relativity, so that you can say, yes, the change in the period and the actual observation of the wave, or detection, I should say, of the waves by LIGO are showing you the same phenomena, namely gravitational waves. So yeah, you're absolutely right that you have to worry a little bit about, not a little, you may have to worry in some cases a lot about
Yeah, it depends on the case. Yes, yeah, it really depends. It
yeah,
varies. Yes.
I hate to use, it depends as an answer, but I think that's the way it actually is. I mean, for example, in the case of Peter Tieberger and his float experiment, I attended a couple of conferences in the 89 and 90 of the Fifth Force Faithful. There were these Morion conferences, and his experiment was subject to enormous critical scrutiny, and nobody could find a mistake. And to this day, nobody knows what's wrong with it. It's just overwhelming. And Nora Boyd has taken me to task for saying that the community was right in rejecting Tieberger. She said we should be a little more tolerant.
Thank you.
I'll just mention we still have 22 people watching. If you want to ask a question, you just put your name in the Q&A box, and we're happy to promote you. In the meantime, while we wait for you to think about that, I've got another question for Allan, if you don't mind. I just want to warn you, this is a completely off-the-wall question. So you might want to just shrug your shoulders and tell me not to waste my time worrying about silly things. There's another area in which the sort of statistical errors that you're talking about have been very prominent, and that's in the stock market. People who work the stock market, they for a while, there was a group that worked with the idea of Six Sigma errors. They would have investment portfolios that would be protected from loss if ever, as long as there was no event of Six Sigma or worse. And things went well for a while until the Six Sigma event came along and wiped them out. What was going on? Well, I think a fair analysis, and again, this is not my expertise, but I think this is what was happening, was the following. The assumption has been that the errors are given by normal distributions with finite variances. Right? There's a kind of plausibility for that because the distribution comes from adding together many small factors, and if those many small factors each have their own mean and variance, then you will end up with a distribution with finite mean and variance, and then you can figure out from just looking at the spread of some existing data what the sigma is. Now the catch is that there might be an error that is distributed with infinite variance. These things can happen, and this, I think, has been Mandelbrot's approach to investing. That in fact you do get errors that have infinite variance, and of course they have much fatter tails when you have an infinite variance. And so things that would look like a Six Sigma outlier, in fact, are quite possible. So I don't imagine that anyone in physics has thought about that possibility. But can we rule out, the possibility that some experiment has an error noise surrounding it that actually has an infinite variance, in which case we would be dramatically underestimating the probability of of outliers. So as I said, a completely off the wall question. So you might not want to
Well,
think about it.
I think there is the possibility of people missing a confounding factor, which would give you maybe not an infinite variance, but certainly a much larger variance. And what can you say about somebody missing something? Is I I remember when I attended one of the Fifth Force conferences. One of the experimenters asked me, shouldn't we double our uncertainty? I like that word better, to take into account unknown factors. And I said, but if it's unknown, why just double it? Why not triple it? And the answer is unknown factors are, in fact, unknown. So you don't know how to quantify them. But yeah, I think it is a problem that people worry about. And I don't know how you,
Yeah.
there are, this is one from, again, my own personal experience. When I was a postdoc in physics at Princeton, we measured the K plus E3 branching ratio, and we sent our result as in those days, a paper preprint to the Berkeley group, which does the particle data. And they came back saying, oh, you're like 2 sigma above the world average. And we said, yeah, it's the best we can do. That's the way it is. And it turned out then that the world average was wrong, because there was one experiment which, when we had a later conference, people admitted had been done incorrectly. So the answer is, yeah, things like that do occur. People make mistakes in calculations. One of the things I didn't mention was internal replications. In the CMS collaboration, typically 3 different groups do the data analysis.
Mhm.
And they're not totally independent because they use the same programs, but the data selection can be different and such. So, yeah.
Okay. So you'll see we've added to our screen Nora Boyd and Dana Matheson. They've both indicated they have questions. So I'm not sure which one of you would like to go first. Nora was the first on the list, so I think it should be Nora, unless Nora and Dana have some agreement that would indicate
I have
otherwise.
no idea what Dana is going to say, so.
Go for it. We can hear you, but we can't see you.
Okay, great. Allan, thank you so much for the talk. It was super interesting. My question is about, I'm wondering if you have a kind of working heuristic for cases where, there are these large discrepancies or discord happening between, results in some like we can think of the beam bottle experiments, for example, or maybe the Hubble tension or other interesting discords. And it seems to me that, the scientist at this point has a choice between, trying to invent new physics to account for that discord, or to, going down the rabbit hole of trying to track down systematics and getting, doing new experiments and trying to get these things to agree. And I'm curious about if you think it's, is it always or usually good to be sort of theoretically conservative and just assume that it's going to be some problem with the experiment and try and track that down? Or do you think the proliferation of new physics at these moments of discord is helpful because sometimes it might work out? Or I'm just curious if you think there's a nice heuristic there.
I have no, I don't think I have advice for the physicists. I think, both are useful things to do. Hunt for systematics and look possibly for new physics, or, it is possible. There's the current problem with G-2 of the mu meson, where the measured value differs from one theoretical calculation by now 5 sigma, according to the latest results. But there's also a different theoretical calculation which agrees with it. And so now we have the discrepancy between the theorists. And they are forming a group, I understand, to try to sort out what the difference is in their calculations. But I have no useful thoughts on the matter of big, like, what do you do with the neutron? It'll be interesting to see if they do it by a third different method. It'll probably come out in the middle, and then nobody will know what's going on.
So I'll just mention, Sloboda and Nora, I'll leave you live. So if you guys want to chip in with anything, and we'll turn to Dana. Can you hear us?
Hi, am I coming through?
You're coming through. We hear you, but don't see you.
Okay. Yeah, thanks, Alan. So I have a question that's related to something that came up in a conversation with a particle physicist about the pentaquark story. And at least from what I recall, you can correct me if I'm wrong, they were saying that there were large discrepancies between measurements that particle physicists and their community were getting compared to nuclear physicists. And both of them were claiming to see some evidence of a pentaquark, but had wildly, or at least significantly different results. And in talking to him about where these differences came from, he said, well, people tried to figure it out. The communities met, tried to hash it out. And nobody could really figure out what was going on there. And he ultimately chalked it up to a difference in culture between the two groups. And that kind of struck me. And I guess I'm curious if you encounter this sort of explanation in other areas, or what you make of people appealing to differences in culture as a way to try to account for these kinds of discrepancies between lines of experiment. Is it a way of just sort of throwing your hands in the air? Is it a kind of substitute for a lack of explanation, or is there something to it? In which case, how do people go about trying to account for differences in culture?
Well, I'm not totally convinced of differences in culture, not because I've been in only two, namely the high energy physics and the history and philosophy of science groups. And so I'm not clear on what a difference in culture would be. I mean, the nuclear physicists, some of them that I knew, took statistics seriously and take the business of selection criteria seriously. And also these days, it's on, some of the people who you might consider nuclear physicists are working at what we used to call high energy physics. They're doing heavy ion collisions and such. And I have nothing useful to say about differences in culture. I think the big thing, I think, was, that in the pentaquark, people were willing to publish results which were shakier than they claimed. But that happens, I think, everywhere. I mean, the first talk I once gave, there was on physics, was when I was a grad student to the journal club at Cornell. And there was people reported, a particle, a 2-pion resonance. And in those days, there were no statistical criteria to speak of. That if you saw a bump, you might report it or not. And, so things change. And I think part of the reason, high energy people now use five sigma is they can. They have so much data. In fact, they have way more data than they can even record. I mean, the number of events recorded as opposed to the number of events produced is like 1 in a million. And so even there, and there's been some very interesting work on that by Corey Caracca and others. So, but you'd have to talk to a good sociologist on differences. Although I once was talking with a nuclear physicist who shall be nameless, who told me that I was successful in my field because people in my field were stupid. So there is some difference in culture.
Oh, well, that's a happy thought. We have another question in the queue from Alexei Moravitsky. I take it you would like to be promoted to ask a question because you've written the text there. So I'll promote you to speak. Is that okay? Or do you want me to just read out the question? Alexei, are you there?
Yes. You can read the question. Well, the question is very short. I'm not a physicist. I'm a mathematical logician interested in philosophy of science and philosophy of physics in particular. And my question is, well, first of all, thank you for the very interesting talk, very insightful for me. But the question is this. Can your examples be considered as illustrations to the old Michael Polanyi's book, Personal Knowledge? Yeah, that's the question.
I would, to understand the question, I would need the particular aspect of Polanyi's book that you're thinking about. Maybe that might help.
Personal knowledge. Personal knowledge.
What in that book are you connecting with what Allan's been
Well,
talking?
he says a lot of, well, the idea of what I grasp reading it long ago, that the discrepancies about which Allan talked, not just accidental, they're normal. This is the normal state of affair in experimental physics. It cannot be eliminated. That's his philosophical point, Polanyi's point. Is it true?
Well, there are often, not always, discrepancies in experimental results, but certainly not always. I mean, the ones that I tended to work on were ones where there was controversy, at least because it's more interesting to see how it gets. I think the methodology of science shows up best when you have a controversy or a disagreement. When everything is going along right, there's nothing much happening. I mean, like in current high energy physics, people are searching for physics beyond the standard model. And it's very boring because they do hundreds of experiments and there's nothing, the standard model keeps working. I mean, Ron and I have talked about this in one of our books. So, yeah, I think discrepancies will occur. One of the things I think one has to remember is that science is a human activity. People make mistakes. People will have disagreements. People will disagree, certainly on theory and also on experiment. There are lots of times when experiments will give, for example, different numbers, like the neutron lifetime. That's going to be, I think, a hard one to fix. But there are other times where, like the T-Burger-Adelberger difference, people just did the experiments more often and with higher precision and accuracy. But no, even T-Burger admits, he published an erratum saying, I must have made a mistake because nobody agrees with me. He says, but I don't know what it is, and nobody else does. Nora has probably lots to say about that.
Thank you.
Well, we have one more question in the queue and very little time left. So Greg, I'll promote you. Can you condense down the question into something shorter than that long paragraph, and then I think we'll be at the end of our time.
Briefly, it's more of a comment. I wanted to know if you, on your gravitational waves, are aware of the pulsar detection of super long gravitational waves that LIGO can't see. There's a new technique where you can find perturbations in the random noise that we've recorded over 50 years in pulsar variations. And we can,
Greg, do you have a radio or something on in the background?
I do. And I was hoping you were going to read my question. Sorry about that. Why don't you just mute me and we'll leave the question where it is. If you can read the question.
It's too long to read. Turn off your radio and just ask a short question.
It's my second Zoom. Sorry. Okay. So let me get out of that. Oh, all right. My question is about pulsars, and have you worked that into your gravitational wave
Okay.
replication
All right.
system?
All right.
The answer is no.
Okay. Fruitful field for future reference as to how this might replicate the whole gravitational wave system that you
Yeah, I mean, by the way, there's a very interesting book called Losing the Nobel Prize about gravitational waves and the BICEP 2 experiment.
Right.
That's a case where they overlooked a source of a confounding factor. But no, I haven't looked beyond LIGO and the Hulse-Taylor-Weisberg case. There are lots of.
Stay tuned and ask Nora. Keep in touch with Nora.
Well, I'm hoping that the G-2 will get resolved, or the neutron lifetime, because it's hard to talk about it without knowing the end of the story, at least for me.
Okay.
Well, I think at this point we've come to the end of our time. Allan, you've been working very hard for an hour and a half now. You must be exhausted. I can see from the background there that you've already planned what you will do next.
No, actually, what's next is lunch.
Oh, lunch. Oh, well, okay. So on behalf of everyone, our thanks to you for a fascinating talk. It is energizing for us all to come back to the original font when it comes to thoughts about experiments in physics and science in general. So please, everyone, if you can do some sort of applausey thing, that would be great. Allan, thank you very much. It's been wonderful to see you.
Thank you. And I'm happy to see people like Nora and Dana who are going well beyond where I went.
Okay. So Sam, are you going to shut things down now for us? Yeah.
Yeah, I can shut everything down.